The next thing we need to talk about are the coefficient estimates, the standard errors, t-stats, and p-values. And remember, these are calculated by the regression output function. We just need to figure out how to interpret them, and we'll look at a little bit on how to calculate them. So the first thing I want to look at is the beta, and the beta is the slope coefficient. Since I have just a single regressor, Excel calls this the S&P 500 because it's the beta on the S&P 500, and it got that because I had a label here. The intercept is the alpha. And so the alpha is equal to 0.0093, and that's per month. So let me multiply, let me just have that be here, 0.993%. I formatted that as a percent. If I multiply that by 12, I annualize it, and I say that, oh, okay, on a risk-adjusted basis, on an annualized basis, over the last 5 years, McDonald's seemed to have earned 11.18% more than it should have. But what I want to know is, how likely is it to have observed this if the answer really is 0? How confident can I be in this value? Because remember, the null hypothesis is this is really 0. So the first thing I do is I calculate the standard error, and that's fairly complicated to calculate. But the t-statistic tells me, remember, the number of standard errors, the coefficient is from 0. So here I have 0.93 divided by 0.0056, and I get 1.67. It means I only need to go 1.67 of these 0.0056s to go from 93 to 0, 1 2/3 of those. That's my t-stat. The p-value is effectively telling me the area under the curve that's outside this area. To get that, I use the t-dist function, and so this is going to equal t-dist, and that's going to be the degrees of freedom, which is the number of observations minus the number of things I'm attempting to estimate. I'm estimating two things, an alpha and a beta, and number of tails. And so this is going to equal the t-dist function of that 1.67. The number of degrees of freedom is 58. It's a two-tailed distribution, and I get 0.10. And the way I interpret this is that there is a 10% chance of observing this value if it really is 0. There's a 10% chance of observing this value if it really is 0. Here's another way to look at it. I can actually take this estimate, this 0.0093, and to that I can add essentially the inverse value from this distribution, which is going to be the t inverse, 0.225, so it's 2.5% in each tail, and again, 58 is the number of degrees of freedom, and I can multiply that by the standard error, and that tells me that I have a 95% confidence that this value, which I estimated at 0.0093, lies somewhere between negative 0.0018 and positive 0.0205. The way to think about that is, since this crosses 0, I can't be 95% confident that this is not 0. I can be 90% confident that this is not 0, but I can't be 95% confident that this is not 0. Again, it's arbitrary to choose 95. We'll just use that in this class. But here I can see that I have to go 5 standard errors to go from 0.6437 to 0. Because the standard error is very, very small relative to my point estimate, I have to go a huge, huge distance to go from this 0.006437 to get to 0. And so therefore, there is a 0% chance of observing this number if it really is 0. And the other way to see that is my 95% confidence interval does not cross 0. So to recap, I have an R squared of 30.40. That means 30.4% of the variation in the return of McDonald's is explained by the return of the market. I have an alpha of 0.0093, which is equivalent to 0.0093% per month, or 11.18% per year. I can be 90% confident that that's not 0, although I can't be 95% confident that that's not 0. And I have a beta for this stock of 0.6437, and I can be 100% confident, or 99+% confident, that this is not equal to 0.